Pilot Handbook. Welcome to the world of aircraft construction, where dreams of flight take shape. Now, let's dive into the basics of what makes an aircraft. Aircraft. Introduction to aircraft categories. Defining flight. In the eyes of the Federal Aviation Regulations, specifically Title 14 Code of Federal Regulations Part 1, an aircraft is any device crafted for flight. We've got quite a lineup under the umbrella of aviation, including airplanes, rotorcraft, gliders, lighter-than-air wonders, powered lift marvels, powered parachutes, and weight-shift control aircraft. Oh, and don't forget the enchanting world of advanced avionics aircraft, those equipped with GPS navigation systems and moving map displays, often paired with autopilot systems. Now, our focus here will mainly be on airplanes, the fixed-wing champs of the sky. For the detailed ins and outs of other fascinating aircraft like weight-shift control wonders, balloons, gliders, powered parachutes, and gyroplanes, dedicated handbooks are waiting to be explored. Design, certification, and airworthiness. Crafting safe skies. When it comes to aviation products, the Federal Aviation Administration takes center stage, certifying three key players: aircraft, aircraft engines, and propellers. To ensure safety, each product dances to the tune of specific airworthiness standards outlined in the 14 Code of Federal Regulations. Let's break it down. Normal, utility, acrobatic, and commuter category airplanes follow the beat of 14 Code of Federal Regulations Part 23. Transport category airplanes sway to the rhythm of 14 Code of Federal Regulations Part 25. Normal category rotorcraft move to the rules of 14 Code of Federal Regulations Part 27. Transport category rotorcraft groove with the guidelines of 14 Code of Federal Regulations Part 29. Manned free balloons float elegantly under 14 Code of Federal Regulations Part 31. Aircraft engines power up within the realms of 14 Code of Federal Regulations Part 33. Propellers spin under the authority of 14 Code of Federal Regulations Part 35. Now, those special classes like gliders and powered lifts don't have their own set of airworthiness standards. Instead, they blend the requirements from various codes of Federal Regulations Parts 23, 25, 27, and 29, creating a unique harmony that suits their design. Once an aviation product proves its compliance, the Federal Aviation Administration issues the Golden Ticket, a type certificate. This certificate comes with a backstage pass, the type certificate datasheet, revealing the nitty-gritty details of the product's design and operation. You can catch a glimpse of these sheets on the Federal Aviation Administration's website. Now, light sport aircraft, including weight-shift control aircraft, balloons, gliders, powered parachutes, and gyroplanes, march to a different beat. Unlike their counterparts, light sport aircraft don't strictly adhere to Federal Aviation Administration airworthiness standards. The Federal Aviation Administration gives a nod to this consensus as the design criteria for these unique aircraft. Light sport aircraft don't dance to the individual tunes of type certificated engines and propellers. Instead, they receive a full-fledged type certificate for the entire aircraft, covering the airframe, engine, and propeller. Manufacturing and airworthiness. Bringing dreams to life. Whether an aircraft is crafted one at a time from design drawings or mass-produced through a Federal Aviation Administration-approved manufacturing process depends on the manufacturer's size and capabilities. Each part undergoes a meticulous conformity inspection during manufacturing to ensure it aligns perfectly with the approved design. Once the aircraft, with its airframe, engine, and propeller, is ready to spread its wings, the Federal Aviation Administration conducts a thorough inspection. Upon passing this scrutiny, the Federal Aviation Administration bestows upon it the coveted airworthiness certificate. This certificate signifies that the complete aircraft meets the stringent design and manufacturing standards, standing tall in a condition fit for safe flight. Think of it as the aircraft's passport to the skies, an essential companion on every flight. Airworthiness certificates come in two flavors: standard and special. Standard certificates, dressed in white, are issued for a range of aircraft categories, including normal, utility, acrobatic, commuter, transport, and special class aircraft, along with manned free balloons. On the other hand, special airworthiness certificates, wearing a shade of pink, make a statement for primary, restricted, and limited category aircraft, as well as light sport aircraft. They also take on roles such as provisional airworthiness certificates, special flight permits, ferry permits, and experimental aircraft. To navigate the skies effectively, a foundational understanding of lift and basic aerodynamics is essential. This chapter serves as a primer for comprehending the major components of an aircraft. For an in-depth study of aerodynamics, refer to Chapter 5, Aerodynamics of Flight. Now, let's delve into the key forces influencing straight and level flight. In the realm of aviation dynamics, 4 fundamental forces come into play: thrust, lift, weight, and drag. Thrust, generated by the powerplant propeller, propels the aircraft forward and opposes the retarding force of drag, caused by airflow disruptions around the wing, fuselage, and other protruding objects. Thrust and drag. Acting parallel to the longitudinal axis, combats drag, a rearward force parallel to the relative wind. While thrust is generally considered to act straightforwardly, nuances in its behavior will be explored later. Weight and lift. Weight, the total load of the aircraft including crew, fuel, and cargo, pulls the aircraft downward due to gravity. In contrast, lift is the dynamic force generated by the interaction of air on the wing, counteracting weight by acting upward through the wing's center of lift. Aircraft axis and control. An aircraft's movements are controlled by manipulating it around its axes. The longitudinal, roll, lateral, pitch, and vertical, yaw, axes govern pitch, roll, and yaw motions, respectively. Center of gravity. The center of gravity is a critical component in aircraft design, representing the point around which the aircraft's mass or weight centers. A well-designed center of gravity ensures stability during flight. However, as the center of gravity shifts rearward, the aircraft becomes more dynamically unstable, emphasizing the importance of maintaining a forward center of gravity, especially in aircraft with front-positioned fuel tanks. Major components. Now, let's take a closer look at the beating heart of every aircraft, the major components that form the foundation of their design and functionality. While airplanes serve diverse purposes, they share common structures that define their overall characteristics. The objectives behind their original designs play a pivotal role in shaping these characteristics. So, buckle up as we explore the key components that make airplanes soar. Overall characteristics and components. Regardless of their intended purpose, most airplanes boast the same major components, each contributing to the aircraft's overall functionality. These components include the fuselage, wings, empennage, landing gear, and powerplant. Fuselage. The fuselage, often deemed the aircraft's central body, serves as a hub for crew, passengers, and cargo. Beyond providing accommodation, it acts as the structural connection for the wings and the tail assembly. While earlier aircraft designs featured open truss structures of wood, steel, or aluminum tubing, modern aircraft predominantly adopt monocoque or semi-monocoque fuselage structures, which we'll delve into further in the following sections. Wings. Wings, those graceful airfoils extending from each side of the fuselage, take center stage as the primary lifting surfaces during flight. Numerous wing designs, sizes, and shapes exist, tailored to specific aircraft performance needs. High-wing planes may feature external braces known as wing struts, while others opt for a full cantilever wing design to carry loads without external support. The mechanics behind lift generation are thoroughly explained in Chapter 5, Aerodynamics of Flight. Wings can be high, mid, or low mounted on the fuselage, with variations like monoplanes and biplanes. Wing components. The backbone of the wing lies in its structural elements, spars, ribs, and stringers, reinforced by trusses, I-beams, tubing, or other devices. These components, working in harmony, determine the wing's shape and thickness. In many modern airplanes, fuel tanks are integral to the wing's structure or housed as flexible containers inside. Control surfaces, ailerons and flaps. At the wing's trailing edges, 2 crucial control surfaces come into play, ailerons and flaps. Ailerons, extending outward from the midpoint of each wing, induce aerodynamic forces for rolling motions. Flaps, located near the fuselage's midpoint, enhance lifting force during takeoffs and landings when extended. Understanding these control surfaces is vital for maneuvering an aircraft effectively. Alternate types of wings. As we explore the diverse world of aviation, we encounter a variety of wing designs tailored to specific flying requirements. These variations play a crucial role in an aircraft's performance, from traditional wings to innovative designs using flexing and shifting controls. Chapter 5, Aerodynamics of Flight, delves into these design intricacies, offering insights into the impact of controls on lifting surfaces. Let's take a glimpse into the fascinating realm of alternate wing types. Weight shift control aircraft. For specific operations like weight shift control, aircraft wings adopt a highly swept design. This deliberate shape aims to minimize drag and facilitates controlled flight by allowing weight shifts. To explore these unique designs further, handbooks tailored to various aircraft categories are available on the Federal Aviation Administration website at www.federalaviationadministration.gov. Empennage, tail group. The empennage, encompassing the entire tail group, comprises fixed and movable surfaces. Fixed surfaces include the vertical stabilizer and horizontal stabilizer, while movable surfaces consist of the rudder, elevator, and trim tabs. Fixed surfaces include the vertical stabilizer and horizontal stabilizer, while movable surfaces consist of the rudder, elevator, and trim tabs. Rudder and elevator. The rudder, situated at the back of the vertical stabilizer, is pivotal for lateral control, steering the airplane's nose left and right during flight. On the other hand, the elevator, attached to the horizontal stabilizer, maneuvers the nose of the airplane up and down. Trim tabs, small movable portions, ease control pressures and can be found on ailerons, rudder, and/or elevator surfaces. Stabilator design. This design, manipulated by the control wheel, operates similarly to the elevator, providing enhanced aerodynamic tail load for controlled movements. An alternative empennage design introduces the stabilator, a one-piece horizontal stabilizer that pivots from a central hinge point. Landing gear and principal support. The landing gear serves as the primary support during various phases, such as parking, taxiing, takeoff, and landing. While wheels are the most common type, airplanes can also feature floats for water operations or skis for snowy landings. Wheeled landing gear. Landing gear with 3 wheels, 2 main and 1 either at the front or rear, defines the conventional or tailwheel landing gear. Alternatively, a nosewheel configures a tricycle gear. Steering is achieved through rudder pedals or differential braking, offering ground control during all operations. The power plant. Engine and propeller. The power plant, comprising the engine and propeller, forms the heart of aircraft functionality. The engine not only powers the propeller but also generates electrical power, provides a vacuum source for flight instruments, and serves as a heat source for occupants. Propeller mechanics. The propeller, mounted at the engine's front, transforms engine rotation into forward thrust. Acting as a rotating airfoil, it leverages aerodynamics to create thrust. Propellers can be adjusted for efficiency based on the angle of attack, AOA, and pitch. The combination of these factors determines the propeller's effectiveness and efficiency, crucial for an optimal aircraft powerplant match. Understanding these major components grants us a holistic view of an aircraft's intricate design. In the upcoming sections, we'll dive deeper into the construction and roles of each component. Until then, let the wings of knowledge carry you forward. If you click like and subscribe and leave a comment, we will provide a coupon for a free PDF download, one of 9 ebooks. However, each individual can only download up to 1 out of 9 ebooks for free.